Hi everyone, welcome back to the Tree of Math. Today we'll be discussing volumes by rotation part 2, where we will go over the shell method. So I'll give you guys the formula right off the bat, and then we'll discuss the intuition behind why this formula works. So the volume is equal to the integral from bound 1 to bound 2 of 2 pi r of x times h of x dx. So with the disk and washer method, the integrand was the area of a circle. With the shell method, the integrand is now the surface area of a shell or a cylinder. So let's see how we can use this in practice. Now, in the last video, we figured out how to find the area generated by this shape rotated about the y-axis. So now the question remains, what about the area generated by this shape rotated about the y-axis? So as it turns out, we can use disk and washer method. It will involve an outer and an inner radius, but we can also use the shell method to solve it, arguably much faster. So this function was y is equal to x squared. So let's first draw out what the shape will generally look like, right? It always helps to visualize things when you're solving area or volume problems. So we have y is equal to x squared, going from 0 to 2. So if we rotate it around the y-axis, the shape will look something like this. Right, so you might imagine the top will be a circle, the bottom will also be a circle. So it'll kind of look like almost a bowl shape. So these sides will slope down to the middle right there. So with that in mind, let's see how we can find the volume of this shape. So as I said, what we're doing with the shell method is we're taking shells of the overall shape as we move out to our bounds, right? So we might imagine that the center is 0, and 2 is somewhere out here, and we're moving our variable of integration across the bounds. And as we're doing so, our shells are gradually getting larger and larger, right, according to the function x squared. So what we want to do is we want to find the surface area of this resulting shell or cylinder. Oops, don't know what happened there. And if we know that we're finding the surface area in our integrand and that our variable of integration is dx, then we also know that the width of the shell would be our differential variable dx, right? So this tiny width right here would be dx. So as we're moving outwards, this dx is moving along as well. So surface area of a cylinder or a shell would be 2 pi rh, right? That's what we have in our integrand. What we need to find out is what r and h are as functions of x. So the radius from the center is pretty easy, right? So at any arbitrary point, in the shape, your radius or your distance from the center or distance from the axis of rotation in this case is just x, right? So let's say x was 1. That's where you're currently, or that's where your dx is currently sitting at. Let's say right now the shell you're looking at is located at x is equal to 1. Your distance from the y-axis is just 1, right? So as you move along, your distance varies linearly with x. So in this case, r of x would just be x. Now what about your height? What is the height of your cylinder? Well, the height of your cylinder varies as you move x outward, right? So as x increases, your height also increases because x squared is an increasing function. So with that in mind, our height of x would just be our function x squared. So as we move outwards, let's say 1.5, your height varies according to the function x squared, or whatever other function your shape is being bound by. So with all of these in mind, we can now calculate the volume as the integral from 0 to 2 of 2 pi. The radius we said was x. Our height of the cylinder, remember the height is x squared dx. Right, and this would give us the overall volume of this shaded region rotated around the y-axis. So v is equal to integral from 0 to 2 pi x cubed dx. We can just use the reverse power rule and take the constants out, so you get 2 pi integral from 0 to 2 of x cubed dx, which is equal to 2 pi times x to the 4th over 4, evaluated from 0 to 2, which is 8 pi. So that's the volume of the shape if we were to rotate this region about the y-axis. Now I said previously that your radius of x always varies linearly with x or y or whatever variable of integration that you use. Right, so let's take our same function, x squared, except this time let's rotate our function around the line x is equal to -1. So we'll still have our bounds at 2, but our lower bound in this case would be -1. So this shape looks even more strange because you'll have something like that. And then you have this hole at the top. And all of these would curve slightly in. So maybe something like a bunt pan, except there's no hole in the middle. It's really hard to describe. Anyway, most things in our integrand remain the same, right? So we still have our bounds -1 to 2, 2 pi r of x, h of x dx. So now, as we're moving along our variable of integration, x, from -1 to 2, what is the distance from any point in the bound to the axis of rotation? Well, let's take a look at x is equal to -1, right? Where you're at the axis of rotation, your radius is equal to 0. Now at x is equal to 1, let's say you're somewhere here, this distance, this radius is now equal to 2, right? So r is equal to 2. Same thing at x is equal to 2, your radius is now 3, because you have to account for this extra distance between the y-axis, where x is equal to 0, and your axis of rotation, where x is equal to -1. So knowing this, we can construct the radius function to be r of x is equal to x plus 1, right? Accounting for this distance between the axis of rotation and x is equal to 0. And of course, your height stays the same, right? Your function, your bounding function, x squared, did not change. So all that remains is to do a slightly lengthier integral. -1 to 2, 2 pi x plus 1 times x squared dx. And you can expand this to be a polynomial and then use reverse power rule to find out what the exact value is. So your radius is always linked to the variable of integration, and it always varies linearly, right? So your radius of x cannot be something like, x squared. So it can't be something like, I don't know, x over 2, right? So it always has to be your variable of integration plus some offset or minus some offset. And that, again, depends on where your axis of rotation is located. So these are the two methods for doing volumes by rotation. You have the disk and washer and the shell method. They both utilize areas in their integrands, except the shell method uses surface area, whereas the disk and washer method uses the area of a circle. I think generally most people would find the disk and washer method more intuitive, as it's more related to the Riemann sums that they've been taught at the start of Calc 1. So we can go over some example problems using the shell method in the next video. As always, thanks for watching, and I'll see you guys next time.